Assalamu alaikum students. Welcome to the lecture number 12 of week 6 of course advanced nanomagnetism. So in this lecture we will discuss the exchange bias effect in thin films and nanoparticles. So uh, what is exchange bias? Exchange bias or exchange anisotropy occurs in bilayers or multilayers of magnetic materials where the hard magnetization behavior of antiferromagnetic thin film causes a shift in the soft magnetic curve of the ferromagnetic film. So it is observed in usually in the antiferromagnetic and ferromagnetic alternative bilayers thin films, and we observe uh, a shift in the hysteresis loop, as you can see in the figure below, that above Tn, when the antiferromagnetic spins are in random direction or in paramagnetic state, we have no shift of hysteresis loop of ferromagnetic system. And on the other hand, on the right panel, you can see if we are below Neal temperature, when the antiferromagnetic system is in the block state and in the antiferromagnetic state, then we have a shift of loop, and this is due to the exchange coupling between the antiferromagnetic and ferromagnetic system. And this is called the exchange bias phenomena. The exchange bias phenomena is of tremendous utility in magnetic recording, where it is used to pin the state of the readback heads of the hard disk drives at exactly their point of maximum sensitivity. So this exchange bias is uh, very famous in thin films and originated also in thin films. So it is actually it is due to the interaction between the antiferromagnetic and ferromagnetic uh, interaction at their interface, and it is observed when the antiferromagnetic system is in the block state. Since antiferromagnetic magnets have a small or no net magnetization due to the antiparallel alignment, so their spin orientation is only weakly influenced by the external magnetic field, because usually we do not need so much high field to orient the ferromagnetic spins, and this field has no effect on the alignment of the antiferromagnetic spins. So a soft ferromagnetic film which is strongly exchange coupled to the antiferromagnetic system will have its interfacial spin spint. So reversal of the ferromagnetic movement will have an added energetic cost due to the interaction with the antiferromagnetic layer. The added energy term implies a shift in the switching field of the ferromagnetic, and the curve is shift looks like the same normal of normal ferromagnetic, but is shifted from the h is equal to 0 axis by an amount of hb, which is the exchange energy. So exchange bias was initially used to stabilize the magnetization of the ferromagnetic layers in reed back heads based on the anisotropy magnetoresistance, which is also called AMR effect. Without the stabilization, the magnetic domain state of the head could be unpredictable and leading to reliability problems. So it was important to fix it. Currently, exchange bias is used to pin the harder reference layer and spin valve read back heads in MRAM memory circuits that utilize the GMR or magnetic tunneling effect. Similarly, the most advanced fixed media are antiferromagnetic coupled to making use of interfacial exchange, this exchange bias phenomena. So okay, so in this picture you can see the hysteresis loop is shifted towards left, and this shifting is due to this exchange bias field, and you can calculate the exchange bias field by this simple formula. The exchange bias is a magnetic phenomena where a hysteresis loop which relates to magnetic response of the material to applied field is shifted relative to the zero field position. So exchange bias like effect was also observed in ferromagnetic nanoparticles due to the MH loop shift observed in the usually in the field cooled protocol. However, the phenomena is not similar to the ferromagnetic and antiferromagnetic thin films. Here it was proposed that the magnetic hysteresis loop of the ferromagnetic core is usually shifted due to the pinning of the disordered spins at the surface of the nanoparticle, which behave similarly or which has the same role as of the antiferromagnetic layer in the thin films, and it is observed drastic shift in the loops. And if to observe this, we usually use to take MH loop in the field cool protocol, which means that we cool the sample above Tn and Tb in some field and go below the Tn and Tb and then take a MH loop to observe the exchange bias like effect in the nanoparticles. The surface disorder spins have different anisotropy as compared to the core spins. So the core interactions in these nanoparticles are responsible for this exchange bias effect in ferromagnetic or ferrimagnetic nanoparticles. So exchange bias effect in these nanoparticles can be investigated by taking two MH loops, one at in the zero field cooling process and one in the field cooling process, and at the same temperature. How you can take the MH loop in zero field cool, you have to cool the nanoparticle sample in zero field from above blocking temperature down to the desired temperature where you want to take the MH loop. Usually the zero field magnetic MH loop is symmetric and does not contain a shift, and in the MH loop, however, there are some reports that there is some zero field cool exchange bias is also present. You can look for the literature, and but a very obvious or drastic exchange bias can be observed in the field cool protocol, and you have to cool the sample in field, usually in few Tesla from above blocking temperature and Tn or Tb in our case to desired temperature. If the field cool MH loop is asymmetric, I mean shifted to left, then you have exchange bias effect, and you can compare it with the zero field cool MH loop to make sure that this is due to the disorder surface. So here as an example, you can see the two MH loops were taken for ferrite nanoparticles. Red one is the 5 Tesla field cooled loop cooled from 350 Kelvin, and the black one is the zero field cooled loop. And you can see in the inset, which is plotted here, is one picture of the coercivity region, and you can see that the red curve is shifted towards left, and a small exchange bias effect is observed. Exchange bias effect depends upon many factors such as on the operating temperature. You can see in the graph the exchange bias effect. The exchange field is plotted as a function of temperature. How you can do this? You have to take exchange bias field cooled loops at different temperatures, and then you can calculate the exchange bias effect for all the temperatures loops, and then you can plot H exchange versus temperature, and you can see with the increase in temperature the exchange field decreases rapidly, and it is due to the fact that with increases the temperature, the thermal energy becomes dominant, and there is thermal fluctuations, and also the surface spins become defrozen, and you lose this coaxial interaction in these nanoparticles. So exchange bias fact also depends upon the cooling field, the cooling rate of cooling field, and the number of cycles of the cooling field in thin films is also depends upon the thickness of the thin films. And I think I motivated you to read more literature about the exchange bias effect and its effect on affected by the cooling field, cooling rate field, number of cycles of the cooling field, etc. So I think it's enough for today, and I hope you have understand the basic concept of exchange bias in nanoscale materials. Okay, Allah Hafiz, goodbye.